At 04:12 a.m. UTC, a coordinated alert rippled across 3 continents. The first signal came from the Atacama Large Millimeter Array in Chile. 12 seconds later, the European Space Network station in Darmstadt confirmed a sudden brightness fluctuation in deep space. Then, at precisely 04:12:19, the James Webb Space Telescope registered something no one expected. Today, the impossible just happened. Interstellar object 3I Atlas, the most scrutinized visitor from beyond our solar system, did not simply fragment, it deployed. Moments ago, astrophysicists confirmed that 3I Atlas released 27 smaller bodies in a near-perfect orbital distribution pattern, forming a widening ring along its heliocentric trajectory at 2.8 astronomical units from the Sun. This changes everything we thought we knew. What we are witnessing is not chaotic breakup, it is structured dispersal. If you want continuous updates on the most extraordinary cosmic events unfolding in real time, subscribe now, because what happens next may redefine our understanding of physics and our place in the universe. For weeks, 3I Atlas had been under constant observation. NASA's Deep Space Network tracked its velocity at 62 kilometers per second relative to the Sun. The European Space Agency mapped its trajectory using high-precision Doppler measurements. Harvard's Center for Astrophysics conducted spectral analysis, searching for volatile compounds typical of cometary bodies. Caltech's Jet Propulsion Laboratory ran gravitational simulations every 6 hours. Hubble monitored surface albedo variations. JWST focused on mid-infrared thermal emissions. Across Chile, Spain, Australia, and Hawaii, synchronized optical arrays measured polarization shifts in reflected sunlight. Never before has an interstellar object received this level of scrutiny. And yet, despite this unprecedented network of instruments, none of us predicted what unfolded. 48 hours before the event, the first anomaly appeared. At 02:03 UTC, spectrographs detected a faint energy surge across the 4.6 micron band, a wavelength typically associated with carbon monoxide sublimation. But the temperature of 3I Atlas remained steady at 213 Kelvin. There was no reason for outgassing. 11 hours later, a second irregularity emerged. The object's rotation period, previously measured at 7.3 hours, shifted subtly to 7.1 hours. Such a change would require internal torque or external force. No debris impact was recorded. No gravitational perturbation from nearby bodies could account for it. 32 hours before deployment, brightness fluctuated rhythmically, not randomly, but in intervals of exactly 17 minutes and 11 seconds. Prime numbers. 17, 11. The pulses continued for 6 cycles, then stopped. 24 hours before the event, JWST captured a faint equatorial band encircling the nucleus, a region with slightly elevated temperature, 7 Kelvin warmer than surrounding material. It formed a thin, luminous seam, a fault line, or something else. 12 hours before deployment, the seam brightened. 6 hours later, Hubble's ultraviolet channel detected microfractures radiating outward in symmetrical spacing. 13 degrees apart, perfect geometry. At 04:12 a.m. UTC, the seam ruptured, not explosively, deliberately. 27 fragments separated from the equatorial band, each with an average diameter of 80 meters. They did not scatter randomly. They accelerated outward at precisely 0.8 meters per second, identical velocity vectors, forming a ring expanding perpendicular to the object's primary axis of rotation. No tumbling, no chaotic spin. Each fragment stabilized its orientation within 3 minutes. We have studied natural cometary fragmentation for decades. Thermal stress produces irregular debris. Tidal forces from planetary encounters create uneven distributions, but no natural process produces 27 equally spaced bodies with synchronized velocity and stabilized spin. No known law of physics predicts this symmetry. Within 11 hours of deployment, the fragments maintained equal angular separation, 13.3 degrees apart, forming what computational models describe as a toroidal orbital structure, an orbit ring. Dr. Elias Moreau at the European Space Agency ran immediate gravitational modeling. His simulations indicated that without active stabilization, the fragments should have drifted by 0.04 degrees due to solar radiation pressure. They did not drift. They held position. Meanwhile, Dr. Anika Rao at Caltech conducted spectral scans of 3 outer fragments. She detected trace metallic signatures, iron, nickel, and something unusual, a narrow emission spike at 1.27 microns that does not correspond to known cometary minerals. At Harvard, Dr. Leonard Weiss proposed a mainstream explanation. Perhaps internal gas pockets formed structural weaknesses along the equator. Perhaps rotational stress created uniform fracture points. It was plausible, but the data resisted simplicity. Because 6 hours after deployment, the fragments began emitting faint radio bursts at 1420 megahertz, the hydrogen line, every 19 minutes, synchronized, not random cosmic noise, not solar interference, synchronized. We ran cross-correlation analysis across 3 continents. The signal-to-noise ratio exceeded 14 sigma, statistically impossible to dismiss as artifact. This was no longer simple fragmentation, it was coordinated activity. 12 hours later, a second anomaly. One fragment, designated F14, dimmed abruptly. Infrared signature dropped from 198 Kelvin to 121 Kelvin in under 90 seconds. Then it vanished from optical and infrared sensors simultaneously. Not drifted, not disintegrated, vanished. Radar reflections ceased, position tracking failed. It was as if F14 had stepped sideways out of detectable space. We recalibrated instruments, we checked for data corruption. There was none. Now 26 fragments remained, maintaining the ring. And then something even stranger occurred. The remaining fragments adjusted spacing, compensating for the missing body. Angular separation shifted to maintain uniform distribution. The ring healed itself. At this moment, the debate intensified. Dr. Weiss maintained that sublimation jets could produce directional thrust, but sublimation is chaotic. It does not produce synchronized vector correction. Dr. Rao proposed an alternative, internal structural anisotropy, perhaps a crystalline lattice distributing stress evenly. Yet no natural lattice emits hydrogen line pulses. Privately, within encrypted communications, a third hypothesis surfaced: technological deployment. I remember staring at the live telemetry feed, watching those fragments maintain their geometry against solar radiation pressure of 4.6 micronewtons per square meter. They were adjusting, responding. 48 hours after deployment, Earth-based magnetometers detected a fluctuation of 3 nanotesla, minor but global. Satellite communications in the Pacific region experienced brief 0.7-second disruptions. Coincidence? Perhaps, but the timing aligned precisely with the fragment's pulse interval, 19 minutes, another prime number, 19, 17, 11, prime sequences. At 2.5 astronomical units, the ring rotated slowly around the Sun, maintaining constant relative orientation to Earth's orbital plane. Why align with us? 3 days after deployment, a second wave of anomalies erupted. Fragments began emitting polarized light in the near-ultraviolet spectrum, synchronized at intervals of 3, 5, and 7 minutes. Prime again. This was no longer random, it was structured. We simulated every natural mechanism: rotational fission, electrostatic repulsion, tidal disruption. None produced persistent geometric stability across 72 hours. Meanwhile, Atacama's radio array detected phase shift modulation within the hydrogen line pulses, subtle variations encoding intervals of Fibonacci ratios: 1, 1, 2, 3, 5, 8. We cross-checked for confirmation bias. The pattern held. Within NASA's Jet Propulsion Laboratory, an emergency roundtable convened. Engineers projected orbital simulations across a curved screen wall. If these fragments maintained velocity, the ring would gradually expand and intersect Mars's orbital path in 18 months. Not collision, intersection, a transit. Were they mapping gravitational wells, sampling planetary magnetospheres, or broadcasting? Across encrypted channels, European and American agencies coordinated silent observation protocols. No public announcement detailed the radio pulses. Official statements described expected fragmentation behavior. Inside control rooms, silence grew heavier. 5 days after deployment, a third escalation. Fragments shifted simultaneously by 0.02 degrees, a collective maneuver, adjusting ring tilt relative to the ecliptic plane. It was subtle, but deliberate. This was no longer passive debris. It was responding to gravitational modeling in real time. Bird migration data from northern Europe recorded slight disorientation patterns during pulse peaks. Amateur radio operators in Australia reported faint interference at 1420 MHz coinciding with fragment emissions. Coincidence layered upon coincidence. And then came the revelation. At 0333 UTC, exactly 1 week after deployment, the fragments ceased radio transmission. Silence for 13 hours. Then, at 1646 UTC, a single fragment, F03, emitted a burst lasting 27 seconds. 27, the original number deployed. Within that burst, encoded phase modulation traced the first 10 prime numbers: 2, 3, 5, 7, 11, 13, 17, 19, 23, 29. No known comet does mathematics. No natural object reconfigures geometry after losing a component. No physics model predicts coordinated orbital ring stabilization without active thrust. And yet, we must remain cautious. Extraordinary claims require extraordinary evidence. Dr. Weiss continues to argue that we may be misinterpreting stochastic resonance amplified by solar-wind interactions. It is possible. Nature often appears intentional when complexity exceeds intuition. But I have spent decades studying the cosmos. I have seen quasars bend spacetime. I have watched gravitational waves ripple through detectors like faint echoes of ancient collisions. This feels different because this system exhibits correction, compensation, persistence. 8 days after deployment, thermal scans revealed microheating at fragment poles, localized 12 Kelvin spikes, suggesting internal energy redistribution. If this is natural, it represents physics we have not yet discovered. If it is not natural, then we are witnessing technology older than humanity. Global reaction remains measured publicly. Privately, contingency simulations explore worst-case scenarios. Could fragments alter trajectory toward Earth? Current modeling says no, but their behavior already defies baseline predictions. In control meeting centers, screens glow through the night. Coffee cups sit untouched as analysts compare spectral lines against mineral libraries. Governments exchange encrypted summaries. No panic, only vigilance. Because the most unsettling aspect is not the deployment. It is the patience. The fragments do not rush. They maintain ring formation, orbiting in quiet precision. As if waiting, as if measuring. Perhaps this is not an invasion. Perhaps it is reconnaissance. Or perhaps it is something more profound. Maybe we're witnessing the early stages of interstellar communication, not a message aimed directly at us, but a demonstration of capability, an introduction written in geometry and prime numbers. For centuries, we have looked outward and asked whether we are alone. Now the universe may be answering, not with words, but with structure. Maybe we're not witnessing the end, but an invitation to expand our understanding of intelligence beyond biology, to consider that technology, once advanced enough, may travel silently between stars, scattering probes like seeds across gravitational fields. The ring of 26 fragments continues to expand slowly, maintaining symmetry. Every 19 minutes, instruments listen. Every day, simulations update. And every night, I find myself returning to the same question. Why 27? Why primes? Why align with Earth's orbital plane? The story is not over.